The concept of a limit is central to calculus. To understand calculus, it is essential to know what it means for a function to have a limit, and then how to find a limit of a function. So we're going to begin by using numerical and graphical approaches to explore the idea of a limit. So calculus can be used to solve certain fundamental questions in geometry, and two of the questions are here. So you can pause the video here and then read it to yourself. These two type of questions are traditionally called the tangent problem, which looks kind of like this. So tangent problem, and the area problem. Today we're only going to concentrate on the tangent problem. In Algebra 1, we were taught how to find the slope of a line, but in this situation, if you look at the tangent line, this red one that is touching the curve at one point, there's only one point on that line that we know of, so we need to do something else to find the slope of that tangent line. So we're going to draw a secant line. Let me erase this, we don't need it right now. We're going to draw a secant line. Secant line intersects the graph at 2 points. So to find the slope of that secant line, we're going to use the slope formula. So m for slope, secant, and to find the slope, it's the change in y's. So in this situation, we're looking at point Q and P. The change in y's, so it's going to be f of x minus f of c divided by the change in x's, x minus c. Notice that this is an x, this is c. So that is the slope of the secant line. But what I want you to notice is that this is the exact same thing as what you learned in Algebra 1. The slope of a line, the slope of the secant line. So now to find the slope of the tangent line, let's look at another figure. So imagine we have three secant lines. We have the first one, second one, and third one. What I want you to notice is that the point, this point here is getting closer and closer to this point on the tangent line. Notice also what happens. The x, it's getting closer and closer to this point here, C. So as the secant line, imagine that it's moving towards the tangent line becomes the limiting position, meaning that's the secant line is going to get really close to it. So as the secant line gets closer and closer to the tangent line, the slope of the secant line is equal to the slope of the tangent line. So if the limiting position of the secant line is the tangent line, then the limit of the slope of the secant line should equal the slope of the tangent line. So what that means is this: as this x is approaching C, then this point Q, it's approaching P, and therefore the slope of the secant line, it's approaching the slope of the tangent line. And in symbols, we write it like this: slope of the tangent line, so m tan, it's going to be limit as x approaches C of f of x minus f of c divided by x minus c. This is the slope of the secant line. Sorry, I said slope of the secant line, but it is the slope of the tangent line. Okay, so now what I want to introduce to you is this notation, which means limit as x approaches C of f of x equals L. L represents some number. Again, limit as x approaches C of f of x equals some number L. Now we ask ourselves, what does it mean for a function f to have a limit L as x approaches some fixed number C? Well, think of it as that the limit of a function is the value and we're talking about the y value, that the function approaches as the x value gets very close to some value of interest. Again, the limit of a function is the value that the function approaches, so we're approaching a y value, as the x value gets very, very close to some value of interest. For example, let's look at these. Now, as we approach, as x approaches c from the right side, then the y value has to be doing something too. It's approaching a certain y value. And if we approach from the left, the y value is approaching a y value, and the limit is just that y value, the L. So basically it's just the y value. So we write it like this: limit as x approaches c of f of x equals to L. What I also want you to notice is that f of c equals to L, meaning that it's defined at c, right there. It's the same exact value. Now, sometimes it's defined at c, but doesn't have the same limit value. Example, as we approach c from the right, the y value is approaching L, that y value. And as we approach from the left, the y values are approaching this y value, L. So the limit exists because we are approaching from both sides a certain y value. So we'll write it like this: limit as x approaches c of f of x equals to L. Well, let me change it because it's g instead of f. That doesn't really matter though, g. But g of c is not equal to L, meaning that when I plug in the value for c into the function, whatever that may be, it's not going to be this y value, it's undefined there. It's going to be this y value up here, whatever that may be. So it doesn't matter if we have a open circle there. We are approaching this y value, and that will be the limit. We also have a case where h of c is not defined. So in this situation, we have h of x. So again, if we approach from the right, the y values are approaching this y value. Let's call it L. And as we approach from the left, the y values are approaching this y value, which is L. So the limit exists because they're approaching the same value from both sides. So I'm going to say limit as x approaches c. This time we have h of x equals to L. But notice that in my graph, if I follow the graph, there's a hole. I have to jump. There's a hole there. And the function is not defined there. So h of c is not defined. So we can have those three cases. Now, what I want to do right now is I want you to pause the video and read this right here. Please, go ahead. Okay, now that you read it, we're going to do a few examples by looking at graphs. So for the following problems, use the graph to investigate three things. So I'm going to read it for you so you can know how to read it. Notice that this time we have like a minus sign, a plus sign, and this one does not have a plus or a minus sign. So what this means is that we want to approach from the left. So negative means from the left. We're coming from the left. That means you're moving to the right. And this one says you are approaching 2 from the right. You're approaching 2 from the right, meaning you're moving towards the left because you're coming from the right. And for this one, you have to check both sides. So here we go. Part A, we're approaching from the left. If I approach 2 from the left, again, 2 from the left, we have to follow our graph. The graph is approaching what? So let me do it again. So I'm approaching 2 from the left, and the graph is approaching what y value is it approaching? That will be 4. So for A, limit Sx approaches 2 from the left of f of x equals 4. So now, for part B, it says from the right. So now we're going to approach 2 from the right. So as we approach 2 from the right, we're going to follow our graph. Our graph is approaching what y value? Again, it's 4. So limit Sx approaches 2 from the right of f of x equals to 4. Notice that when x is equal to 2, you're there. So when x is equal to 2, your y value is 2. It's not 4, it's 2. We are approaching, as we get closer and closer to 2 from both sides, we are approaching 4. But the actual value, when x equals 2, is 2. So finally for C, let me write B here, oops. For C, limit Sx approaches 2 of f of x equals 2. Now earlier I said that if it does not have a plus sign or a minus sign, we have to check the left side and the right side. So the limit Sx approaches 2 from the left is 4. The limit Sx approaches 2 from the right is also 4. So therefore, the limit Sx approaches 2 is 4. So in order for the limit to exist, the one-sided limits, these are called one-sided limits, have to be equal to each other, and they are. Okay, let's go on to number 2. Same thing, we're going to be looking at Sx approaches 2 from both sides. Let's start with the left side. Now, let me use colors. So our key point here, our point of interest is 2. Okay? Now, as we approach 2 from the left, let's follow our graph. So if I follow the graph, it looks like it's approaching this y value, 4. Again, as we approach 2 from the left, follow your graph, and it's approaching this y value. It's approaching it. We're not saying it's equal to, it's approaching it. So now we're going to write it. So for A, limit Sx approaches 2 from the left of f of x equals, we said 4. Now, we want to approach 2 from the right. As we approach 2 from the right, follow your graph. Follow your graph. What y value is it approaching there at 2? So the limit is 2. Sx approaches 2 from the right. So B, limit Sx approaches 2 from the right of f of x equals 2. So the one-sided limits are different. So what that means is this, that if I want to find the limit Sx approaches 2 of f of x, I have to look at the one-sided limits. From the left, it's equal to 4. From the right, it's equal to 2. Since the one-sided limits are different, we say that the limit does not exist. D and E does not exist. That's what we have to write. D and E. The one-sided limits have to be equal to each other. If not, the limit does not exist. And I think you knew that because you kind of read this already. Now, let's see. More graphs. Use the graph to investigate the limit Sx approaches C of f of x. If the limit does not exist, explain why. So we're going to look at C. This time they did not tell us to approach from the right or from the left. They just said C. But we have to do both, no matter what. So let's see. Let's approach C from the left. If I approach C from the left and I follow my graph, it looks like it's approaching 1. So the limit Sx approaches C from the left of f of x equals to 1. Okay, now let's check from the right. As we approach C from the right, follow your graph. What y value is it approaching? Again, it's approaching 1. So limit Sx approaches C from the right of f of x equals to 1. What that tells me is since the one-sided limits are equal to each other, the limit exists, and we can say the limit as x approaches c of f of x equals to 1. Let's look at the next one. Okay, let's approach c from the left. Notice we follow our graph, and it looks like it's approaching 1. Now let's approach from the right, and notice that it is approaching the y value, which is 2. So that means that since the one-sided limits are not the same, we say that the limit as x approaches c, let me write it better, of f of x does not exist. Let's do one more. Same thing, we're going to approach from the left first. So if I approach from the left, what's my graph approaching? It's approaching 1. And if I do the same thing, but this time from the right, and I follow my graph, it looks like it's approaching 3. So the one-sided limits are not the same. So we say that the limit as x approaches c of f of x does not exist. Now what I want you guys to notice is this. Notice that where the limit does exist, it looks to me like if I keep drawing, if I draw with 2 pencils or 2 markers, whatever you want, they end up touching each other, and that will be the limit. But if I use 2 pencils or markers, whatever you want, and I draw, I notice that they do not touch, or they're not going to go to the same y value, so therefore the limit does not exist. Same thing here. Notice that we're approaching 3 from this side and 1 from this side. They don't touch or get close to touching, so therefore the limit does not exist. Okay, let's go on to the last example using graphs. So suppose the function f has the graph shown. So this is the graph of the function, and it has several x values here, a, b, c, d, e. Notice here there's a break, there's a hole here. But anyway, let's see. Investigate whether or not each of the following limit exists. So all we have to do is say yes or no. Yes, it exists. No, it doesn't exist. So let's start. So this first one, a, we want the limit as x approaches a from the left. We're approaching a from the left. Let's approach a from the left. If I approach a from the left, is it approaching something? Yes, it's approaching this y value. What is it? I don't know. It doesn't matter, but it exists. So yes. Now, for b, it says that to approach from the right. We need to approach from the right. Let's approach from the right. If I approach from the right, my graph is approaching a y value? Yes, it is. Yes. Okay. Now, for this one says x approaches a. It doesn't tell you from the left or from the right. So that means you have to check both left and right. And if I go back, notice that from the left and right, they're approaching the same y value. And therefore, we can say that the limit exists. Yes. Okay, now, let me erase this so it won't get all crazy. Now, we need to approach b from the left, b from the right, and then b to see if it exists. So let's approach it from the left first. So if I approach b from the left, I follow my graph. Is it approaching a certain y value? Yes. So it exists. Now we want to approach from the right. If I approach from the right and I follow my graph, is it approaching a certain y value? Yes. Okay, good. Now, for this last one, as x approaches b. Yes, from the left, it does have a limit, it exists. From the right, it does have a limit, it exists, but are they the same? And notice that they're not. They're not the same. So therefore, for this one, we can say that the limit does not exist, d and e. Notice that for when we were approaching a, if we use those two pencils, pens, markers, whatever you want to call it, your fingers, you're approaching the same y value from both sides. And if you look at b, notice that they're not going to touch. You're approaching different y values. So therefore, the limit does not exist at b, even though it exists from the right and the left. So now let's look at d. We were going to approach d. Now that tells me that I have to approach from both sides. It doesn't tell me from the right or left, so I have to do both sides. So let me erase this. Okay, so now let's approach d from the left. So as I approach d, and then approach it from the right, are we approaching the same y value? Yeah, so that means it does exist, yes. And then the last one, e. Now we're going to approach e. Let's approach e from the left first. So as I approach e, let me draw a vertical line so I know where to stop. So that would be there. So as I approach e from the left, and then as I approach e from the right, we are approaching the same y value. So the answer is yes. So it doesn't have to have an open circle or a closed circle. That is a closed circle. So it doesn't matter. Here, even if there's a, we call this a cusp, still they're approaching the same y value from both sides, so the limit does exist. Okay, now we're done with graphs. Let's look at how to find the limit by using a table. So let's see. Here we want to know what is the limit as x approaches 2 of x plus 3. So here's my table. And we want to get really, really close to the value of 2, x. So here's my x. These are all the x's. And the y value is basically our function. So what we want to do is plug these values into my equation to see what we get. So let's see what happens when I plug in a 1.9. Basically it means 1.9 plus 3. That's going to be 4.9. And then if I add the next x, 1.99 plus 3, that's going to be 4.99. And then the next one's going to be 4.999. That's from the left. Now let's try it from the left. I'm going to start with the outermost one, this one, 2.1, since we're moving to the left from the right. So if I add 2.1 to 3, we get 5.1, 2.01 to 3, 5.01, and 2.001 to 3, we get 5.001. So to me, it looks like as we approach 2 from the left and we're approaching 2 from the right, it looks to me like it's getting closer and closer to 5. So the limit as x approaches 2 of x plus 3 is 5. That's all there is to it. Okay, next example. This time we want to find, let's read it together. So the limit as x approaches -1 of this function. Again, x approaches -1 of this function. So what we want to do is plug in these x values. Notice that they're getting closer and closer to -1. They're getting closer to -1. So all you have to do is really just plug it into the calculator and let's see what we get. So plugging it in, this is what we're going to get. So it'll be 3.31, 3.0301, and then this one I'm gonna write it below, you can't really see it, 3.003001. Okay, now let's do from the right. So we're approaching from the right. If I plug in that 0.9, we're going to get negative, I'm sorry, it's not negative, it's positive 2.71. Then if I plug the next number in, we get 2.9701. And if I plug in that last one, we get 2.997001. So to me, it looks like as we approach -1 from the left, and as we approach it from the right, it's getting closer and closer to 3. So that means that the limit as x approaches 1 of this function is going to equal +3. That's it. Okay, last example. This time we want to find the limit as x approaches 1 of this function right here, natural log of x divided by x minus 1. So we start by plugging in these x values to the calculator. And when we do, we're going to get some kind of long values, so I'm going to rewrite them here somewhere. Let's see. So if I plug in this 0.9, we get 1.0, 5360. Then if I plug this one in, we get 1.00503. And then if I plug this one in, we get 1.0050. Okay, now let's start on the other side. If I plug in this 1.1 into the function, we get 0.95310. Then if I plug in the next one, we get 0.995033. And then if I plug in this last one, we're going to get 0.99, another 950. So once we analyze it, and I notice that as we approach 1 from the left and we approach 1 from the right, the y values are getting closer and closer to 1. So that tells me that the limit of this function as x approaches 1 is going to give me 1. And that's it, ladies and gentlemen.